Way back in 2017, I was using my Nikon D5300 to image the Iris Nebula. I was taking 200-second exposures at ISO 1600. This is a screen capture of the image viewer feature in CaLIGHTs. Here I am displaying what one light frame looks like before calibrating. I've zoomed in to the upper left of my light frame to display some stars, some cosmic dust, and the edge of the Iris Nebula down at the bottom right corner. I have turned up the image stretch to maximum, which really makes it look horrible, but you will see it helps to display the camera's dark current. You can see lots of noise throughout the image. You might see horizontal and vertical colored lines in the image. These are not real. They occur because of the high resolution of this image and trying to show this on a YouTube video. The way astrophotographers deal with this noise is to stack several light frames, which dramatically reduces the random noise. In 2017, I was struggling with differential flexure. CaLIGHTs dark optimization came to the rescue for me, but I want to show you what would happen if I didn't use a master dark. Here is a stack of 26 light frames that continues to look horrible. I didn't calibrate the light frames, I just stacked them. I chose the maximum stacking mode, which is great for seeing satellite trails or hot pixels. In this case, you can see lots of red, green, and blue streaks. These are caused by hot pixels. The squiggly lines are caused by differential flexure. Differential flexure causes oval stars to appear in our astrophotos. It also causes each light frame to be slightly offset from the previous light frame. When Deep Sky Stacker aligned the light frames using the stars, the hot pixels created these squiggly lines. These squiggly lines are often called walking noise. The squiggly lines clearly indicate what direction the walking noise took in my stacked image. Here is the same stacked 26 light frames, but here I chose the average stacking mode. The red, green, and blue squiggly lines are much fainter. All I did here was to change to the Kappa Sigma stacking mode. For this mode, the aligned pixel values for all 26 light frames are sorted pixel by pixel, and the highest and lowest values for each pixel are discarded. This mode is great for eliminating hot and cold pixels, satellite trails, and gamma ray strikes. This is normally the best result for stacking, but you can now clearly see the walking noise streaks. The block ADU logic in the DSLR had done its best to eliminate the average accumulation of electrons caused by dark current, but that's clearly not good enough. These are not hot or cold pixels, they are dark current. The truth about dark current is that each individual pixel has its own unique electrons per second accumulation rate. This variability of accumulation rates looks like noise, but it's not random, it's predictable. Better still, it can be calibrated out of your light frames by using master bias and dark frames. I use the CaLIGHTs dark optimization feature to apply a 305-second ISO 1600 master dark frame and an ISO 1600 master bias to the 26 light frames. All the light frames were 200-second exposures at ISO 1600. CaLIGHTs determined the exact amount of the master dark frame to apply for each of the 26 light frames. Just before I display the resulting Kappa Sigma stacked image, I want to mention that my Nikon D5300 does have amp glow. It causes the left side and the top of the image to appear brighter. You will notice that these areas will become darker when I apply dark optimization. Another benefit of using a master dark frame. you can still see some of the walking noise in this image. Let's remember that this image is very strongly stretched. As each of us progress through this hobby, you will eventually begin imaging very, very dim deep sky objects. When you do, dark current will be waiting for you. Okay, let's take a different approach to understanding dark current. I'm going to attempt to compare the dark current performance for 4 different cameras. I was able to obtain bias and dart frames, as well as master bias and DARKS for a Canon 750D and for an ASI 2600 MC Pro. I also included my Nikon D5300 and my QHY 294C. In order to do this comparison, I was able to standardize on ISO 1600 for the 2 DSLRs. I used a gain of 1600 for my QHY 294C, which is the gain where the camera operates using its high gain mode, also called HGC mode. The gain for the ASI 2600 MC Pro camera was 100, which is where this camera switches to its HGC mode. Each camera has unique electronics and software, so I had to invent a method to compare them all. The only reason we care about dark current is because it creates noise in our astro photos. This noise looks like specks of light sprinkled all over our light frames. This observation gave me the idea that I could treat the dark current as a source of light photons that make our light frames look noisy. To do this, I needed to convert the pixel values in the dark frames into what they represent in photons. Doing this for each camera would allow me to make comparisons. In this table, I attempted to calculate a scaling factor that will relate the pixel values to their equivalent in photons. For DSLRs, I went to the DxOMark website and retrieved the Unity ISO, pixel size, and quantum efficiency, or QE. For a DSLR, the Unity ISO is the ISO at which an increase of 1 count in a pixel's value corresponds to 1 electron. The QE indicates how efficiently your camera can convert photons into electrons. For astrocams, I went to the vendor's site and retrieved the effective full-well and QE. The effective full-well is the number of electrons that fit into each pixel before that pixel value reaches its maximum value of 65,535. I included the equations I used for your convenience. Unfortunately, I was not able to get master darks for each camera that were the same exposure. In order to compare master darks from each camera, I need to invent a multiplier that takes this into account. In order to do this, I need to examine master bias and darks from each camera. I will quickly go through how I did this. Because this is a video presentation, you can always rewind the video and pause to study each slide if you wish. First, we will look at the master bias for my Nikon D5300.